Welcome back to another lesson in physics. In this lesson, we're going to be studying the electric current. What we've learned up to this point on electric circuits is that electric circuits are all about energy consumption. The voltage is the electric potential difference across the external circuit that provides the electrical energy that gets used up in a circuit. When a battery or other voltage source no longer works, it has used up its internal energy source. Batteries that we buy at the store use chemical potential energy to create electric potential energy. Once the chemical potential energy is depleted, there's no longer a potential difference in the external circuit, so the circuit won't work. Voltage is the electromotive force that pushes charge in a circuit. Charge can be thought of as the source that moves the energy through the circuit. The battery or other voltage source does work upon the charge to place it at a high electric potential energy. The charge is the medium that allows the electric potential energy to move through the circuit and be transformed into other types of energy, such as heat energy, light energy, sound energy, and mechanical energy. Charge is already in the circuit, waiting to be pushed along. When the voltage source is turned on, it sets up an electric field that turns on at the speed of light. When the electric field turns on, charge everywhere throughout the circuit begins flowing at a very slow rate of about 1 centimeter every minute. So how is it that you can flip a light switch and the light comes on almost instantaneously? It's because the charge is already sitting there next to the light bulb. And when you flip the switch, you're providing the energy, the push to get these charges moving. The charge moves together very, very slowly, like soldiers marching in a line. When the charge re-enters the negative terminal of the battery, the charge then becomes re-energized via the internal circuit of the battery, and the march starts all over at the positive terminal. Okay. Here I have a circuit. Here's a battery that's going to supply 6 volts of electric potential difference in the external circuit. So I have the positive terminal connected with this red wire that goes to a switch that you can turn on and off. Right now I have the circuit off. When I close the switch, the circuit comes on. Then I have a wire that connects the switch to the bulb, connects to another bulb, and then this black wire is being used to connect to the negative terminal. So, circuit is closed when the switch is closed. The circuit is open when the switch is open. So the circuit will convert electrical energy into light energy. I think I have a fan in here somewhere. So here I have set up a circuit similar to the one I drew on the board over here. Except in this circuit, I'm using 2 6-volt batteries. And when you connect 2 6-volt batteries in series, you end up with 12 volts because the voltage of the 2 batteries adds together when they're connected in series. It's hard for you to see, but I do have a wire that connects to a switch, and then the switch connects to one lamp, which connects then to another lamp, which is then connected to a fan. So when I close the switch, circuit, charge can then flow. Open the switch, and the charge quits flowing. So what I've been talking about the past 2 days is how you have to have a voltage source in your circuit in order for the circuit to work. The voltage source provides the oomph, the force, the push that gets the charge flowing. But as we said, the charge is already right here in all these conducting wires. It's already there. Charge is not being pumped out by the batteries or the voltage source. A lot of people mistakenly think that charge gets pumped out by the voltage source. That's incorrect thinking. The voltage source does act like a pump, but it acts like a water pump, for example, in your sinks. If you think about your kitchen sinks, when you turn the sink on, is water being pumped all the way from the water municipal in the city? No, the water is already sitting right there in the faucet, and when you turn the water on, the water comes out. Similar to these batteries here. They provide the push, the oomph, to get that charge that's already in these wires flowing. So the charge is already there, and what we're going to be talking about in this video is how the current in the wires, which is the charge flowed in the wires, does move very slowly. It moves as slow as 1 centimeter every minute. So the question I'm asking you then is, why is it that you turn the switch, you close the switch, the circuit comes on, and instantaneously the light in the fan comes on? That's because the voltage source, the electric potential difference in the external circuit sets up an invisible electric force field that turns on at the speed of light. And that force field gets the charge flowing. What, Reagan?
Dude.
What?
You're weird. You're like.
The battery provides the oomph to get the charge flowing. EMF, electromotive force. Once all the chemical juice inside this battery gets used up, the circuit will no longer work. The charge will not flow, and the circuit will not work. As long as the battery is providing a voltage source, charge will flow through the circuit. Electric current is the name that we use to define how fast charge flows past a point through a circuit. So current is a rate, and it's the rate that charge flows at a single point in a wire. We can express current mathematically with the equation charge divided by time. The symbol for current that we use is the letter I. C is used for coulombs, it's used for capacitors, and so they've chosen I to represent current. So capital I represents current, and since current is equal to charge, we use Q to represent charge divided by T for time. The SI units for current is named the ampere. You'll see it called the amp, and you'll see it abbreviated capital letter A. 1 ampere is equal to 1 coulomb per second. 1 amp equals 1 coulomb per second. Current is a rate quantity. If you could isolate a small cross-section area of the wire in a circuit and measure how much current flows in a second, in that area you would have electric current. So this diagram here represents what I'm talking about. You isolate a single point in a wire and you find out how much time it takes for the current to move in that single point. And that is what we mean by current. For example, if you were to isolate this part of the wire and measure the current that flows in this part of the wire and time it, and it took 40 seconds, and you measured the charge to be 2 coulombs, that would be a current of 2 coulombs for every 40 seconds, which has a unit rate of 1/20th of a coulomb per second, which is 0.05 amps. By convention, we define current to flow in the direction from the positive terminal to the negative terminal. So we are assuming the electric field is set up to cause current to flow in the direction that a positive test charge would flow. This convention dates back to Benjamin Franklin from the 1700s when he studied electricity. Benjamin Franklin did not know about electrons and protons, and he thought that electricity flowed like a fluid. He envisioned positive charge as the charge carrier. As such, this convention that charge flows from the positive terminal to the negative terminal of the battery is the convention that all scientists and engineers use throughout the world today. It does not matter that the actual charge carriers are the electrons. It's a convention that you get used to as you study electricity in greater depth. Charge drifts through the wire rather slowly. It flows at a rate of about 1 meter for every hour. So here I have a diagram, and I want to show you what I mean by the fact that it drifts slowly. So if you represent the charge in the wire with this line here, it zigzags. For every 2 steps forward, there are 3 steps backwards. So it zigzags through the wire. We call that the drift speed of the charge. A large current does not have anything to do with the drift speed. Rather, a large current has to do with the amount of charge that is moving at any given second through a point. This is the same as saying it is the density of charge flowing through the wire at a given point that determines the current. Take a look at these 2 diagrams. The one on the right is showing a much larger current. This is due to the fact that there's a much larger density of charge as compared to the diagram on the left. So these red dots here are representing the charge carriers. Charge carriers do not have to travel a long distance in a short period of time to have a high current. Rather, current has to do with the amount of charge traveled in a second at a certain point in the wire. A thicker wire will allow a greater current. If you go to the store like a Home Depot or Lowe's and you buy a lower gauge wire, like a 10 or 12 gauge wire, those electrical cords are going to have more charge carriers and will allow you to have a higher current compared to if you were to buy a higher gauge electrical cord like a 14 or 16 gauge. Those electrical cords are going to be thin compared to the 10 and 12 gauge, and they're going to allow you to only have a small current at any given time. The lower the gauge number, the more current that is allowed in that wire. The higher the gauge, the less current you're going to get with that electrical cord. Thanks for tuning in. I hope you're learning a lot about electric circuits. So far, you should have a pretty good understanding of voltage and current in an electric circuit. And if my videos aren't helping you learn it, please go to thephysicsclassroom.com and study and read and try to gain a greater understanding of electric circuits. Have a great day. Bye.